Okay, our next talk will be given by Hiroki Furue, and he will be talking about an improved Postman information set decoding algorithm towards more efficient time memory trade-offs. Yeah, please.
Thank you for the introduction. I'm Hiroki Furue from NTT Social Informatics Laboratories, and today I'll talk about an improved Postman information set decoding algorithm towards more efficient time memory trade-offs. And this is joint work with Yusuke Aikawa from the University of Tokyo. And first, let me briefly explain contributions. Information set decoding is one of the most efficient frameworks for solving the syndrome decoding problem. And this is used as a basis of code-based cryptography. And Botmay algorithm is known as asymptotically fastest ISD. And in this work, we propose a variant of the Botmay algorithm, achieving more efficient time memory efficient trade-offs between the time and memory complexities. And this is the outline. First, I'll talk about the background of my research. Currently used script systems known to be not secure against quantum computing attacks, so we've addressed the research on post-quantum cryptography, and among these candidates for PQC, in this work we focus on this code-based cryptography, which is constructed based on the difficulty of the syndrome decoding problem. And this is the definition of this syndrome decoding problem. As input, we are given three positive integers, n, k, w, and parity n-k by n matrix H over the binary field, and n-k dimensional vector S. And then in this program, we try to find vector E satisfying these equations, He equals S, and having weight of this E equals W. And for example, in the case of n equals 8 and k equals 4 and w equals 3, the inputs are given like this one as the matrix over the binary field and n-k dimensional vector S. Then for this input, this is a solution, and we can confirm that because the sum of these three columns corresponding to these three non-zero elements is 1, 0, 1, 1, and this equals S, and the weight of this E equals W. So this is a solution for this input. And this code-based cryptography is playing an important role in NIST's PQC standardization. Actually, this HQC is selected as a CHEM to be standardized from code-based schemes, and further in the competition for additional signatures among 40 round 2 candidates, these cross and less code-based schemes. So it's very important to evaluate the security of code-based schemes for the standardization of PQC. Next about information set decoding. This information set decoding ISD is a framework for solving SDP based on linear algebra and combinatorics. And this is performed in the following steps. In the first step, we choose a permutation matrix P, and this is an n by n matrix. We choose this one randomly and multiply this from the right side to a given matrix H. And in other words, this P shuffles the distribution of a solution vector E by multiplying P inverse, because like that, H dot E equals HP dot P inverse E. And in the second step, we compute matrix n minus k by n minus k matrix Q, such that the QHP has like this one. The left side is identity matrix with size n minus k, and then we denote the right part by as h1. And then the target equation h dot e has been changed into like this form: qhp dot p inverse e equals qs. And now we are trying to find a vector corresponding this part p inverse e from the transformed inputs qhp and qs. Then in the third step, we try to find such a vector. And we set parameter p. And for this p, we find the vector e prime. This is a k-dimensional vector satisfying these equations. And wt of e prime equals p. And wt of h1 e prime plus qs equals w minus p. Then if we find such a vector e prime, then we can generate a solution from this e prime. And we here suppose that the vector, n-dimensional vector, whose upper part is h1 e prime plus qs, and the lower part is e prime. Then when we multiply this vector to qhp, and this equals h1 e prime plus qs, because the left part of qhp is an identity matrix, and plus h1 e prime, and so this equals qs. So this satisfies the equation of this qhp dot p inverse e equals qs. And further, this vector also satisfies condition for the Hamming weight, because the weight of the upper part is w minus p and the lower part is p. So the weight of this vector is w. So this vector recovered from e prime can be solution. But in some cases, we cannot find such a vector e prime in this third step, so we have to repeat these 3 steps until we find a solution. And this means that we repeat choosing the permutation p until the distribution p inverse e satisfies the conditions for Hamming weight. And in this talk, we mainly deal with asymptotic complexity, and we estimate this complexity like the following method. When we are given the size of the matrix n, then we set k as like this k equals k hat n, and we take this k hat as a worst case rate for the time complexity. And in many ISDs, this k hat is approximately 0.45. And then we compute w as h inverse of 1 minus k over n, and this h is a binary entropy function. And this setting is called as full distance decoding, and we can expect that there exists one solution. And for these parameters, we compute the complexity in the form of 2 to alpha n plus O1, order 1, and this alpha is constant value, and take this value alpha as its complexity. And actually, like as this figure shows, here shows the time complexity of these main ISDs, and the first one is Brange's algorithm proposed in 1962, and its time complexity is 2 to 0.121 n. And today, the light one, BM algorithm is known as the fastest one, with time complexity 2 to 0.0951 n. And from a more technical point, in ISD, we use a search tree to find the vector E prime in this third step. And actually, for example, we first prepare some subsets of the k-dimensional vector space like this from L01 to L04. Then we merge these lists and generate a second level list, L11 and L12. And actually, this L11 is generated as a subset of the sums of L01 and L02. And like this way, we merge these lists, and finally we get L21 and check every element of this L21 for being a solution or not. And this method is known to be more efficient than the exhaustive search on the vector space, k-dimensional vector space. So many ISDs use this method. And more specifically, we generate such a tree by each level list, considering each layer of QHP. And we here denote by H01, H11, and H21 each layer of the submatrix H1 of QHP. And actually, when we generate the first level list from L01 to L04, we use conditions determined from H01, and we use the second level list from the information of H11, and we use the final list L21 from H21. And more specifically, for example, in the case of L11, we generate this L11 from L01 and L02 by checking the value of H11 dot x plus y, and where this x is an element of L01 and y is an element of L02. And like this way, we construct the search tree in ISD. And actually, for these main ISDs, the five schemes, these five schemes use actually use the search tree, but there is a difference of method to merge lists. Actually, the DUMAS and MMT and BJMM algorithms use birthday search to merge lists in the search tree, but these MO and BM algorithms use nearest neighbor search to merge lists, and these MO and BM devise the time complexity by using this nearest neighbor method. And in this work, we mainly focus on this time-memory trade-offs. And in practical situations, the memory consumption is a major bottleneck of ISD. And so in Eurocrypto 2023, Escher and Zweidinger proposed variants of MMT and BJMM with efficient time-memory trade-offs. So please see this figure. And this x-axis shows a memory exponent, and y-axis shows a time exponent. And actually, when we can increase the memory upper bound for the memory complexity, we can reduce the time complexity like this. And when we focus on these two red lines for the BJMM algorithm, this solid red line is original BJMM, the complexity of the original BJMM algorithm, and the dotted red line is time memory trade-off version of this BJMM. And at the most light point, where we can use sufficient memory size, the time complexity is the same between these two algorithms, but at left points, their proposed algorithm can reduce the time complexity from the original algorithm. So this means that their proposed algorithm achieves more efficient time memory trade-offs compared from the original algorithms. And actually, they propose an efficient time memory trade-off version for this MMT and BJMM using the birthday search to construct the search tree. But for these two algorithms, MO and BM, using the nearest neighbor, it's been open program whether it is possible to construct efficient time memory trade-offs. So in this work, we addressed this problem. And so next about our contributions. In this work, we propose a new variant of the BM algorithm, achieving more efficient time memory trade-offs. And we construct this algorithm mainly by applying the techniques of Escher and Zweidinger. And actually, this figure compares the performance of the original VM and this the blue line and the proposed VM and orange line, and this green line shows time memory trade-off version of BJMM. And when we compare the original VM algorithm and our proposed version, at the right point, the time complexity has the same value. But in the middle point, the time complexity of the proposed algorithm is smaller than the original version. And further, when we compare the proposed algorithm with the time memory trade-off version of BJMM, at any points, we can reduce the time complexity. So we can, by the proposed algorithm achieves more efficient time memory trade-off curves compared with existing algorithms. And from a technical point, we construct the proposed algorithm by using these two techniques. The first one is to relax the constraints for parameters and change the way of constructing the search tree. And at the second point, we change the way of taking the permutation matrix. And about the first point, when the permutation matrix P satisfies a condition for Hamming weight, the original VM algorithm set parameters such that we always find a solution using the search tree with probability 1. But in the proposed algorithm, we relax this constraint such that the probability that we find solution is lower than or equal to 1. And by doing so, we can choose parameters more freely to minimize the time complexity. And we compensate this decrease in probability by increasing the number of iterations. And we use the efficient way method to repeat the generation of the search tree. In the proposed algorithm, we mainly use the search tree with degree 4, but we here use the tree with degree 3 for simplicity. And in the original algorithm, if we cannot find a solution at the final list, L21, then we reconstruct all lists from the first level. But in the proposed algorithm, we only reconstruct a higher level list by changing some conditions, and we use the same previous lower level list. And by doing so, we can reduce time complexity for each iteration. But there is an upper bound of the number we can repeat the generation of the higher level list. And we estimate this bound of the iteration number from the success probability of the nearest neighbor search. And at the second point, we change the way of taking the permutation matrix P. As I said before, we construct the search tree considering the condition determined from each layer of the submatrix of QHP. And when we focus on the first level list, only these left part and right columns are related to this first level list because the right part includes H01 and the upper left block is an identity matrix. And so if we cannot find a solution in L21, then we can reconstruct the higher level list only by taking permutation matrix only applied to the central part, because that doesn't affect the left and right side part. So by doing so, we can reconstruct only higher level list using the same lower level list. And when we consider this second technique, we can further increase the upper bound for the number that we can repeat the generation of the higher level lists, compared with the case that we only consider the first technique. And by using these techniques, we construct this proposed algorithm, achieving more efficient time memory trade-off curves. And finally, we conclude this talk. In this work, we proposed efficient time memory trade-offs for the BM algorithm. And the proposed algorithm is more efficient in the case where the memory complexity is limited. And our future work is to analyze the effect of the proposed techniques on the bit complexity, mainly used to estimate the security of specific parameters. And that is, thank you very much.
Any questions for the speaker?
Hi, Hiroki. Yeah, thanks so much for a great presentation.
Thank you.
I noticed you use depth layer 2 in your estimator for the algorithm. Have you considered how your algorithm performs with depth layer 4, the recommended version of the Booth-May?
You mean about the
In the search tree?
search tree? You mean about the degree of the search tree?
Oh, no, the depth level.
Depth. Okay,
Yeah,
okay,
yeah.
okay. Yeah. In this work, we mainly use the tree with depth 4, and in general, the depth 4 version is considered to be most efficient one, because if we further increase the depth, then the gain is a little bit. So the depth 4 version is not the best, the best one, and we also use the depth 4 version to build the variant of this VM. Thank you.
Any other questions? Okay, I have one small question. So how do you consider the cost of memory accesses?
Yeah, you mean with the memory complexity, memory consumption of this algorithm?
I mean, in the literature, I think there are many different ways to define the cost of one memory access. Like some people say that this is, I don't know, cube root of the memory size or
Okay.
something.
So actually, as I say, in practical situations, memory consumption is a major bottleneck. So actually, the proposed algorithm could be more efficient in the case where we can only use a small memory size. Yeah. So that is our result. Yeah.
Okay, thank you. If there's no question, then let's thank the speaker again.